All right, now we're on to the last section of Chapter 6, which is Section 6.3. And in this section, we're going to talk about what is known as the central limit theorem. When we use the normal distribution to find the probability of a continuous random variable, we specifically look at how an individual data values varies about the mean of the population. However, sometimes statisticians wish to look over how a sample of data varies about the population. In this case, we look at the distribution of the means of each of the samples, which now becomes our random variable. So in last chapter, we had our random variable x was distributed normal with a mean of mu and a standard deviation of sigma. And in this section, we're going to look at what is the distribution of the sample mean. So we're going to look at the distribution of x bar. And we'll talk about that right now. The sampling distribution of the sample means is a distribution using the means computed from all possible random samples of a specific size taken from a population. So what it should look like is, say for instance here, I have my population, and I'm going to take random samples from this population of some size. And here are all these samples. Then from each of these samples, I can then compute the sample mean x bar for each of these samples. And if I keep doing this an infinite number of times, then these x bars will have a distribution, just like when we had with the data values x had some distribution. Now, when we take a variable from a sample, the mean of the sample will differ from that of the population, because we're not taking all the individuals of the population, so we're not going to get an exact measure of the population mean, because the measure of the sample is not the same as the population, just like we mentioned a second ago. Now, this phenomenon we call the sampling error. And that should make sense. There's going to be some error in between the sample and the population, because it could possibly not be an accurate representation of the population for every sample we take. Now let's look at this. This means that the mean and standard deviation for the sampling distribution. So we're going to look at what is known as the mean of the sample means. What does that mean? That's just what we talked about over here. For each of these samples from the population, I'm going to compute some sample mean x bar. And then at the end, whenever I have taken the infinite number of samples from this population and calculated each individual sample mean from that sample, then at the end, I will compute that mean of these means. And we're going to say that the mean of the sample mean, so mu of x bar, is equal to mu. So in our case, we had x was distributed normal mu sigma. And in this case, x bar is going to be distributed normal mu, still has the same mean, but we'll talk about the standard deviation here in a second. And the standard error of the sample means we will denote by sigma of x bar. So sigma of x bar is equal to the original sigma we had divided by the square root of the sample size. And this part right here is true if our random variable originally, so if this x up here, our random variable, from the population is distributed normally. So that means up here, then in this part, the standard deviation, instead of sigma, will be sigma over the square root of n. Now, how is that going to affect our z-score formula? Remember from the previous section, we had z is equal to the data value we're looking at, x, minus the mean, and then divided by the standard deviation. Then using that same idea here, the data value we're beginning looking at is actually a sample mean. So this is going to be the given sample mean that you're interested in. Then you're going to subtract off the mean of that distribution of the sampling means, mu x, and then divide by the corresponding standard deviation, sigma of x bar. And we just said above that mu of x bar is equal to mu, and sigma of x bar is equal to sigma over the square root of n. So therefore, this formula becomes x bar minus mu divided by sigma over the square root of n. So our formula is going to slightly change here when we're interested in what's the probability of our sample mean falling in between two values or less than some value. And to summarize, if we have x is distributed normal with some mean mu and some standard deviation sigma, then x bar, so the distribution of the sample means, will be distributed normal with that same mean mu, but a standard deviation of sigma over the square root of n. Next, a very important theorem comes up from this sampling distribution, and we're going to call this theorem the central limit theorem. And what does it state? Okay, so the central limit theorem states if the sample size n is large enough, and how are we going to define large? If n is greater than or equal to 30, then the sample mean x bar will have an approximate normal distribution with the mean mu and standard deviation sigma over the square root of n, just like we had on the previous page. And that's no matter the shape or distribution of the data. So as long as our sample size is greater than or equal to 30, then the distribution of the sample means will be normal with this mean and this standard deviation. Now, another key fact we'll talk about here, as the sample size gets larger, so as n goes to infinity, the distribution of x bar approaches the normal distribution. And that's what we mean by it has an approximate normal distribution. As the sample size increases, it's getting closer and closer to a normal distribution. Now we're going to look at two scenarios. First one, if the data values x, so this is the random variable we're looking at, is assumed to be approximately normally distributed, then the probability of the sample means x bar can be found using the sampling distribution of the sample means. And what is that distribution? We just talked about it on the previous page. It was normal with a mean mu and a standard deviation sigma over the square root of n. The next scenario, if the data x is not assumed to be approximately normal, then the probability of sample means x bar can be found using the central limit theorem. So CLT is the shorthand for central limit theorem, and this is going to apply if our sample size is greater than or equal to 30. And that's just using this up here. If our sample size is greater than or equal to 30, then we can say the distribution of the sample means is approximately normal with this mean and this standard deviation. And in both scenarios, we have that the distribution of the sample means is approximately normal with a mean of mu and a standard deviation of sigma over the square root of n. And we can find the z-scores by using the formula on the previous page. Z is equal to the sample mean we're looking at of interest, x bar, minus the overall mean of the sample means mu, divided by its corresponding standard deviation, sigma, over the square root of n. Now what happens if x isn't assumed to be normally distributed and our sample size is less than 30? That makes it easy. We can't do anything in that case. But if it actually this data x follows some other distribution, then we could find the associated probabilities, but we're not going to talk about it in this class because that's going to go beyond the scope of our course. Now, although our formula slightly changed here, we will still use the same method as in section 6.2 to calculate the probabilities by turning the individual sample means we're looking at into z-scores and then finding the associated probabilities in our standard normal table. Now, let's look at an example to illustrate this. Number 1. The average age of a vehicle registered in the U.S. is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their average is between 90 and 100 months. Now, the way we know we're going to look at the distribution of the sample means is we say find the probability that the mean of their age. It mentions the probability of the mean. Then we're going to be looking at the distribution of x bar. Now, let's first decide what our random variable x, which of the data values is going to take on. So, x is going to be the age of the vehicle. And what is the distribution of x? It doesn't say in the problem, so we're just going to say x is distributed. We don't know the distribution, but it has a mean of 96 and a standard deviation of 16. And that's for just our random variable x. Now we're going to look at what x bar is. So x bar in this case will be the mean age of the vehicles. And what is the distribution of x bar? So we don't know the distribution of x in this case, So then we can't use the previous rule on the previous page and say that this distribution is normal, but we can use the central limit theorem because our sample size is greater than 30 and say that the distribution of the sample means is approximately normal with the same mean as before of 96. But in this case, it has a standard deviation of sigma, which was 16, divided by the square root of n. And n in this case was 36. And this is by the central limit theorem. Now let's kind of determine what the problem is asking. So we want to find what? The probability of the sample mean being between 90 and 100 months. That means we want the probability of x bar being in between 90 and 100. Now, how did we do this in the previous section? We found the z-scores associated with these two values, and then we looked at the area in between them. Let's do that same idea applying it here. The first step was draw the normal curve and shade the appropriate region. And I would highly recommend doing this. It just makes it easier to determine which area you're actually looking at. And also, it just makes the problem a little bit easier. And it may show up on the exam, so I would emphasize doing this first step. So draw the normal curve. And if we do that, we have x bar, so the distribution of our sample means is approximately normal, so it has a bell shape. It has a mean in the middle of 96. And we're interested in what's the probability of it falling between 90 and 100. That means we're interested in the area in the middle right here. Then we can find it by finding the z-score associated with the sample mean of 100 and the z-score with the sample mean of 90. Now let's do that in the second part. We want to convert these two sample mean values into z-scores. So convert 90 and 100 into z-scores. Let's look at, say, z1 is the z-score corresponding to the sample mean of 90. Let's say x bar minus the overall mean mu divided by sigma over the square root of n. I'm just writing here to emphasize to you what the actual sample mean we're looking at is. In this case, we're looking at the first sample mean of 90. We're subtracting off the overall mean of 96 right here. And then we're dividing by the corresponding standard deviation of 16 over the square root of 36. Now recall that our standard normal tables will only give us up to 2 decimal places. Then we're going to round this to negative 2.25. And that'll be the z-score associated with the sample mean of 90. Doing the same thing for 100, we have z2 is equal to the sample mean we're interested in, which is 100, minus the overall mean of the sample means, which is 96. And then again, divided by the corresponding standard deviation of 16 over the square root of 36. And this to 2 decimal places is 1.50. Now for the final step, we want to find the probability. I'll write it this way. So the probability of getting a sample mean in between 90 and 100 months is the same as getting a z-score in between negative 2.25 2.25 and 1.50. And we talked about how to do this in the last section, or actually in section 6.1. We look at the probability of z being less than the higher z-score minus the probability of it being less than the lower z-score. Then using that idea, I want to look at the probability of z being less than or equal to 1.50 and subtract off the probability of z being less than or equal to negative 2.25. Now let's just use the table since this is the first example in this section. The probability to the left of 1.50 is 0.9332. It's right here. So that's 0.9332. And the last one, z of negative 2.25. So we do negative 2.2 and then over to 0.05. That is 0.0122. 0.0122. And if we take the difference of those two, we get 0.9210. And that is our answer we were interested in. That means the probability of getting a mean of their age between 90 and 100 months is equal to 0.9210. And that is it for the first example. Now let's look at the second one. It says the average time spent by construction workers who work on weekends is 7.93 hours. Assume the distribution is approximately normal and has a standard deviation of 0.8 hours. What does that mean? Here it is telling us that let x be the number of hours worked, or you can say time spent working. And it tells us this distribution. It says it's approximately normal, so x is approximately normal with a mean of 7.93 hours. So mu is 7.93. And sigma, the standard deviation, is 0.8. Now let's look at the first part. Find the probability that an individual who works at that trade works fewer than 8 hours on the weekend. It doesn't say find the probability that they work on average fewer than 8 hours. It just says works fewer than 8 hours. That means we're interested in the probability of x being less than 8. And if we draw the curve like we did earlier, here you have the distribution of x. It is approximately normally distributed. It has a mean in the middle of 7.93. And we're interested in what's the probability of x being less than 8. We're interested in this area over here. Then let's convert this 8 right here into a z-score first. Then z is equal to the data value we're interested in, which is 8 hours. 8 minus the mean, which was 7.93. And then divided by the standard deviation, which was 0.8. And then rounding this to 2 decimal places, this gives us 0.09. Then that says the probability of x being less than 8 is the same as the probability of getting a z-score less than 0.09. And we can find this area in the table easily. Just go to 0.0 and then over to 9, and that is 0.5359. 0.5359. And that is our answer for the first part. Now, let's look at the second part. If a sample of 40 construction workers is randomly selected, find the probability that the mean of the sample will be less than 8 hours. In this case, it's saying find the probability that the mean of the sample will be less than 8 hours. So we're dealing with the distribution of the sample means. Then in this case, x bar will be equal to the mean time spent working and I want to emphasize here, this x bar is a capital X bar, and this is the random variable. The little x bar we'll look at here in a second will be 8. That's the sample mean we're interested in looking at, find the probability of it being less than that. Then we had in the previous part that this distribution was already approximately normal. So that implies that already the distribution of our sample means is normal, with the mean still the same of 7.93 and a standard deviation of sigma divided by the square root of n. Sigma in the original problem was 0.8, and it tells us if we sample 40 construction workers, so that implies n equals 40. So our standard deviation of the sample means is 0.8 over the square root of 40. Now in this part, we wanted the probability of x being less than 8. In this part, we want the probability of x bar being less than 8. Now I'm not going to draw the picture here because it's basically the same. Instead, this x is x bar. So we're still looking at the area to the left of getting a sample mean of 8. Then let's use the z-score formula to find corresponding to a sample mean of 8. So it would be this little x bar, the sample mean we're interested in, minus the mean mu, and then divided by sigma over the square root of n. And if we plug that in, the data value we're interested in, which is the sample mean of 8 hours, minus the overall mean of 7.93 hours, and then divided by the standard deviation, 0.8 over the square root of 40. Into 2 decimal places, this is equal to 0.56. Then that means the probability of x bar being less than 8 is the same as the probability of z being less than 0.56. And this we can find in the table, and if you look for it, it is 0.7213. And that is how you find those two areas. And that would be our final answer we want. So that is all for section 6.3. We will go over a little review real quick, and then we'll actually be done with chapter 6. This first one, it says the average number of gallons of lemonade consumed by a football team during a game is 20 with a standard deviation of 3 gallons. Assume the variable is normally distributed. When a game is played, find the probability of consuming the following. Let's first determine what our random variable x is and its distribution. So x, the variable of interest, is the gallons of lemonade drink per game. So we're just going to say the gallons of lemonade. And now we want to look at the distribution of this. And it says, assume the variable is normally distributed. So x is distributed normally with a mean of 20, because they drink on average 20 gallons per game. So mu is 20. And what is the standard deviation? It has a standard deviation of 3 gallons, so sigma is 3. Let's look at this first part. Find the probability of consuming between 20 and 25 gallons. That means we want the probability of X being in between 20 and 25. I guess we'll draw it pictorially for this first example. That would be, say here we have the distribution of X. Here in the mean, in the middle we have the mean of 20. And up here, say we have 25. We're interested in the area between these two. Then we can convert both of these values to z-scores just like we did before. And then look at the area between those two z-scores. Then the first one we're going to look at is the z-score corresponding to 20. So z1 is equal to the data value of interest 20 minus the mean, which is actually 20, and then divided by the standard deviation of 3. And notice that this is actually equal to 0 because 20 is actually the mean. Now let's look at the next one, z2. The data value we're interested in this case is 25. Then we have 25 minus the mean of 20 divided by the standard deviation of 3. Into 2 decimal places, this is 1.67. Now we have the two z-scores. We want to find the area in between these two. Then we have the probability of X being in between 20 and 25 is the same as the probability of Z being in between 0 and 1.67. Then using the same idea, we want to take the probability of Z being less than the higher z-score minus the probability of Z being less than the lower. And that would look like the probability of Z being less than or equal to 1.67 minus the probability of Z being less than or equal to 0. And this first one, the probability of Z being less than 1.67, so we go 1.6 over here, and then 0.07 is 0.9525. This is 0.9525. And that's just this probability right here. We need to subtract off the probability of Z being less than 0. And if we look in our standard normal table, for 0, the area to the left is 0.5. And that means we're going to subtract off 0.500. Now if we do that, we get a final probability of 0.4525. And that is the answer for the first part. Now let's look at the next one. Find the probability of consuming less than 19 gallons. In this case, we just want the probability of X being less than 19. Then using the same idea here, we can draw the picture. We have here the distribution. We have the mean in the middle is 20. And we're interested in the area to the left of 19 because we want to know the probability of it being less than 19 gallons. Then we're looking at this area to the left of 19 right here. Then let's find a z-score corresponding to 19 first. To do that, we have z is equal to the data value we're interested in, 19, minus the mean of 20, divided by the standard deviation of 3. Into 2 decimal places, this is negative 0.33. Then that implies the probability of X being less than 19 is the same as the probability of Z being less than negative 0.33. And we can find this value in the table. And doing that, so negative 0.33 is right here, 0.3707. 0.3707, and that is the final answer we're looking for. Then that is how you do the first problem on the Chapter 6 review. Now let's look at the second one. It says the mean undergraduate cost for tuition, fees, room, and board for a 4-year institution was $26,489 for a recent academic year. Assume sigma is $30,204 and that there were 36 4-year institutions sampled. Find the probability that the sample mean cost for 36 schools is the following. In this case, find the probability that the sample mean cost. That means we're looking at the distribution of x bar. Then in this case, our random variable x bar is the mean cost. And what is its distribution? It says x bar is, we don't know the distribution actually yet in this problem, but we do know the sample size is greater than 30. Then we can say the distribution of the sample means is approximately normal with the same mean as x has, which is 26,489. So that means this is 26,489. But the standard deviation is equal to sigma over the square root of n. So that would be 3,204 divided by the square root of n, which was 36 because we sampled 36 schools. Then let's look at this first part. Find the probability that the sample mean cost for these 36 schools is less than 25,000. That means we want the probability of x bar being less than 25,000. If we want to draw that out graphically, we can do that as well. Here you have the distribution of x bar. It's approximately normal, and it has a mean of 26,489. So 26,489, and 25,000 should be roughly around here. And we're interested in the area to the left of that because we want the probability of getting less than 25,000. And here was 25,000. The next thing we want to do is use the z-score formula to find the z-score associated with the sample mean of 25,000. And that would look as follows. Z is equal to the sample mean we're interested in, 25,000, minus the sample mean of the sample means, so it's just the overall mean of 26,489, and then we divide by the standard deviation, which is 3,204 divided by the square root of 36. And if we do that to 2 decimal places, this z-score is negative 2.79. Then that implies the probability of getting a sample mean less than 25,000 is equal to the probability of getting a z-score less than this one we got, negative 2.79. And we can look up this area in the table already because we're looking at the left-hand area. And this will give you 0.0026. And that is the answer we're looking for here. Now let's move on to the next part. Find the probability that the sample mean cost for these 36 schools is greater than 26,000. That means we want the probability of x bar being greater than 26,000. Let's draw that out graphically to figure out how we're going to do that. Then we have the distribution of x bar is approximately normally distributed. And we said it has a mean of 26,489. So we'll say 26,489. The probability we want is the probability of getting a sample mean greater than 26,000. Say, for instance, we have 26,000 is right here. 26,000 is right there. We want to look at the area to the right of this because we want to know what's the probability of getting a sample mean greater than 26,000. And how will we find this? First thing we want to do is find the z-score associated to 26,000. So doing that, we have z is equal to the sample mean we're interested in, 26,000, minus the overall mean of 26,489, divided by the corresponding standard deviation of 3,204 divided by 36. And this is equal to negative 0.92. That means the z-score right here associated with 26,000 is negative 0.92. Now, let's look at this. So that means the probability of x bar being greater than 26,000 is the same as the probability of getting a z-score greater, so this is a greater than sign, negative 0.92. But our table will only give us the left-hand area. So to find the right-hand area here, we want to take this left-hand area and subtract it from 1. So that would look like we'd have 1 minus the area to the left of this z-score. So the probability of z being less than or equal to negative 0.92. And then if we look up this probability in the table, so negative 0.92 is right here. That's 0.1788. Then our probability is equal to 1 minus 0.1788, and that gives us a final probability of 0.8212, and that is our final answer. And that is it for the end of Chapter 6. I will see you all in class next week for Chapter 7.